Hello everyone, today we are building something really cool, a classic analog clock using C++ and raylib. This is a fantastic little project you can complete in a single evening, and it is perfect for learning some key C++ and raylib concepts while creating something practical and fun. Remember, to become a good programmer, it is essential to build as many projects as possible, even simple ones. Each project teaches you something new and helps you grow as a developer. Let's jump in and start coding. Today we are making a cool analog clock. I know it might look a bit tricky now, but don't worry. We are going to break it down into 7 super simple steps. Trust me, by following along, you'll have your own working clock before you know it. In order to be able to follow this tutorial, I expect you to have a basic knowledge of the C++ programming language and a development environment for C++ already installed. I am going to work with Visual Studio Code. Also, we are going to need the raylib library. I have prepared a detailed video on how to install raylib on your Windows computer and use it with Visual Studio Code. You can watch it here. It will help you set up everything on your Windows computer. If you prefer to use Visual Studio, check out the second tutorial I have prepared. It will be linked in the video description. If you use a different operating system, you can still follow this tutorial if you have a working C++ setup with the raylib library. We will also be using object-oriented programming to keep our code clean and organized. If object-oriented programming seems challenging or you want to master it, check out my comprehensive object-oriented programming course where I break down everything you need to know, also linked below. Now let's start with step number 1, which is to create a blank screen and set up the main loop. Before we start, it is important to understand the structure of today's project. It consists of 2 parts. The first part of the code is where we define our variables and initialize essential objects like the clock. The second part is the main loop, which is responsible for displaying the clock and updating the time. The main loop is like the heartbeat of the project, running repeatedly until the project is closed. Now let's create a blank screen and the main loop. Let's open the C++ starter template for raylib that I have created with VS Code. You can download this template project by visiting this GitHub repository. If you open this template with Visual Studio Code, you can see it is organized in folders. We have to open the source folder and double-click on the main.cpp file. If we now compile and run this project by pressing F5 on the keyboard, it displays a bouncing ball example. Cool, our setup works. We are ready to start developing our project. Let's delete the ball.h and ball.cpp files and all the code from the main.cpp file. Just leave the include raylib line and the main function just like I did. Now let's create a blank screen for our application and the main loop. First of all, we have to create our main window. The main window is like a black canvas where we can draw our objects. We need to specify the width and the height of the main window. Let's create 2 variables to hold the screen width and screen height for our window. I am going to use a size of 600 by 600 pixels. Const int window width is equal to 600 and const int window height is equal 600. To create the main window, we have to call the initWindow function. This function initializes a window and takes 3 arguments: the width and the height of the window and the title. InitWindow, parenthesis, window width, comma, window height, comma, quotes, analog clock. Now, every time we create a window, at some point we have to destroy it, and we do so with the closeWindow function. So let's add the closeWindow function here. Perfect. We just created the window, and to draw on it, we use a coordinate system similar to the one taught in high school. Each point on this window has its unique x and y values. The coordinate system used in computer graphics differs from the standard Cartesian coordinate system taught in high school. In computer graphics, the origin of the display is located at the top left corner, with 0, 0 being at the top left. In contrast, the standard Cartesian coordinate system starts from the bottom left corner, with 0, 0 being the origin. In this system, the x-coordinate increases as we move to the right, and the y coordinate increases as we move up. However, in the top left corner coordinate system used in computer graphics, the x-coordinate increases as we move to the right, and the y-coordinate increases as we move down. This means that a point at 10,10 will be located 10 units to the right and 10 units down from the origin. We will be using the top left corner coordinate system today. That's why it is important to understand the differences between these two coordinate systems. The basic setup of our project is ready. Let's now work on the main loop. Let's write a comment first. Main loop. The main loop consists of three parts. First, event handling. First, we check for any events, such as the user attempting to close the application or interacting with it, for example by pressing some keys. Second, updating. Next, we update the state of our clock. This involves retrieving the current time from the system. Third, drawing objects. Finally, we draw the clock components, including the face and the hands, in their updated positions on the screen. This step uses raylib's graphics function to render the clock visually. By following these three steps, we create a dynamic analog clock that continuously updates in real time and reflects the system's current time. Now let's implement these three steps. We start the main loop with a while loop like this: while, parentheses, and curly brackets. The while loop is an essential part of our project. It runs continuously until we close the app. At each iteration of the loop, we perform three key steps: checking for events, updating the state of the analog clock, and drawing the clock. Let's place some comments to help us organize our code inside the main loop. 1. Event handling goes here. 2. Updating state of the analog clock goes here. And 3. Drawing the clock goes here. The while loop will run over and over again until we close the app. The first thing we do inside the while loop is to check for any events. Now, inside the parentheses, here we type the condition. Window should close, parentheses, equals false. The window should close raylib function is a very useful function. It checks if the escape key on the keyboard is pressed or if the close icon of the window is pressed, and returns true if that is the case. So, if it returns true, the main loop ends and the window is destroyed. Our main loop needs two more functions. First, we need to call the begin drawing function in the drawing part of our main loop. This function creates a blank canvas so we can draw our game objects on. Next, we need to call the end drawing function, which ends the canvas drawing. Lastly, there is something else we need to do. We have to define how fast our project should run. We do so by calling the setTargetFPS function before the main loop. The setTargetFPS function takes an integer as an argument, which represents the maximum number of frames per second we aim to achieve. Typically, games run at 60 frames per second, but for our analog clock project, we will set it to 15 frames per second. 15 frames per second is enough for our analog clock because the clock only needs to update once every second to move the second hand. Using a higher frame rate, like 60 frames per second, would waste computer power without making the clock look any better. So, outside of the main loop, we type setTargetFPS parentheses 15. This means that the while loop and all the code inside it will run 50 times every second at most. This setup doesn't guarantee our simulation will run at exactly 15 frames every second. Rather, it sets 15 FPS as the ceiling. This means our simulation won't run faster than 15 FPS, but it could run slower, depending on the system's capabilities and the complexity of the scene being rendered. Now that the main loop is complete, we can run the application for the first time. As you can see, nothing is inside the simulation window because we haven't drawn anything yet. But the important thing is that we can see the application window with the title and the dimensions we defined, and that we can reliably close the application by clicking on this X icon here. Beautiful. The application window is black. Let's make it a light blue color. Raylib provides several built-in colors, but we will be defining our own colors for this game. In Raylib, colors are represented using a struct called color, which contains 4 unsigned byte components. red, green, blue, and alpha. The values for each component range from 0 to 255, where 0 represents the absence of the color and 255 represents the full intensity of the color. For example, to create a red color, we will create a color struct with the following values. Color red is equal to curly brackets 255, 0, 0, 255. The first three values represent the red, green, and blue components respectively, while the fourth value represents the alpha component, or the transparency of the color. In this case, the alpha value is set to 255, which means the color is completely opaque. So, to create a light blue color at the top of the file, let's create a color struct like this. Color light blue is equal to curly brackets 225, 239, 240, 255. Inside the main loop, before the end drawing function, we call the clear background function. Clear background, parenthesis, light blue. So when the clear background function is called, the Windows background is cleared with this light blue color. This is typically done at the start of each frame of the main loop, so that the previous frame's graphics are wiped clean and the new frame can be drawn without any old artifacts or remnants. If we run the simulation now, we can see the simulation window is now light blue. Beautiful. We just completed a very basic main loop, so we can remove step number 1 from our list. We have made progress. Now let's work on step number 2. Let's design our clock phase. An analog clock is made up of several key parts, each playing an important role in displaying the time. Let's take a moment to understand the structure of the clock as a whole before we dive into creating its phase. Our analog clock will consist of the following components. 1. The clock phase. This is the foundation of the clock. It includes the outer rim, the main phase, and the hour markers. It serves as the base for the clock hands and helps the user read the time easily. 2. Clock hands. These include the hour, the minute, and second hands. Each hand will rotate around the center of the clock and update dynamically to display the current time. 3. The center dot. This small dot in the middle of the clock serves as the pivot point for the hands, answering them visually to the face. Now that we understand the overall structure of the clock, let's focus on creating the clock phase as it forms the foundation for everything else. Here is what we will build in this step. First, the outer rim. This gives the clock its bold, circular outline. To make it visually interesting, we will use a two-tone design with a dark gray outer layer and a light gray inner layer. This layering adds depth and makes the clock look polished and professional. Second, the main phase. Inside the rim, we will add a white circle that acts as the clock's background. This clean, neutral base makes the hands and the hour marks easy to read. Let's start. In this project, we are going to use object-oriented programming to help us organize our code. In object-oriented programming, we group related data and functionality into classes, which makes our code more modular, organized, and easier to maintain. So let's create an analog clock class. We are creating a separate class for our clock, so we need to separate the declaration of the class and its implementation. This is where the header file and the implementation file come into play. The header file contains the class declaration, including the class name, member variables, and function prototypes. It serves as an interface for other parts of the program to use the class. On the other hand, the implementation file, usually with a .cpp extension, contains the actual implementation of the class functions. This is where the member functions declared in the header file are implemented. Separating the class declaration from its implementation allows for better organization and abstraction of code, making it easier to manage and maintain large projects. So we will need to create two new files. To create the analog clock class, I press Ctrl+N to create a new file and then Ctrl+S to save it as analogclock.hpp. I will use the .hpp extension to distinguish the C++ header files from the C header files which have the extension .h. Now we can start writing the header file of our analog clock class. Pragma once. This is an instruction that ensures that this header file is only included once in a compilation unit to avoid duplicate definitions. Now we can declare our class. Class analog clock, curly brackets and a semicolon. Public colon, private colon. The class will have a constructor. Analog clock, parentheses and semicolon. Now let's think about what attributes and methods our class needs to have. We need to be able to set the size of the clock, so it will have a size attribute. Let's make it private. Int size. The size attribute represents the radius of the clock in pixels, and it will be used to determine the dimensions of the clock phase. Next, we need to position the clock on the screen. For that, we will add a private attribute position to store the x and y coordinates of the clock's center. The obvious way to implement this is to use x and y attributes for the position, but there is another way to do it which will make our lives easier. The vector2 struct the raylib library offers. You can think of it as a data structure that contains x and y attributes, the same attributes that we want for our class. Let's use a vector2 variable to hold the position of the clock object. So let's include raylib in our header file. At the top of our file we add include raylib.h. Now we can use the vector2 struct vector2 position. Now it is time to modify our class constructor to take two parameters, the size of the clock and the position on the screen. This way, every clock we create can have its own unique size and location right from the start. So inside the parentheses we add int size, vector2 position. Let's also initialize the attributes of our class using the initializer list. In C++, the initializer list is a part of the constructor that allows for direct initialization of the attributes before the constructor's body executes. This is not only a cleaner way to write code, but also more efficient, especially for complex objects. Here is how we can do it. We add the following here: size, parentheses size, position, parentheses position, and curly brackets. This expression initializes the size attribute with the value provided as the argument size. And this expression does the same for the position attribute using the position argument. Our constructor is ready. For now, we also need another method, the draw method. The draw method will handle rendering the clock on the screen. Let's declare it. Void draw, parentheses, const. We declare the draw method as const to ensure it does not accidentally modify any of the class attributes. Our class structure is ready. Now let's work on the fun part. Let's create the clock phase. As we said, the clock consists of some simple shapes. First, let's create the outer rim. Let's start implementing the clock phase in the draw method. So far, we have only created the header file. We also need to create the implementation file. One quick way to do it is to put the mouse over the unimplemented draw method. As you can see, VS Code notifies me that this method is not implemented. We can click on the Quick Fix button and then select the first option to create the .cpp file and the definition. Perfect. This saved us some time. We will need two colors for the outer rim, a dark gray and a light gray. Let's create them here. Color dark gray is equal to curly brackets 45, 45, 45, 255. Color light gray is equal to curly brackets 229, 229, 229, 255. Now in the draw method, let's draw the outer dark circle. That's very easy. We will draw a filled circle using the drawCircleV function. drawCircleV, parentheses, position, size, dark gray. This function requires three arguments to draw a circle. Position, a vector2 specifying the center of the circle on the screen. Size, the radius of the circle in pixels, determining the size of the outer rim. And a color. Here we define the color of the circle, a dark gray shade with full opacity. This function will render a solid dark gray circle that acts as the outer rim of the clock phase. Let's run our code so far to see our analog clock for the first time. Let's go to the main.cpp file. First, let's include the analog clock header file. Include analogclock.hpp. Now let's create an analog clock object. Analog clock, clock. Now we need to give the clock a size and a position. Let's give it a radius of 250 pixels and position it at the center of the screen. So we type here curly brackets 250, curly brackets 300, 300. Next, let's go to the main loop and call the draw method of the object. After we clear the screen, we call the draw method, clock.draw. Perfect. Let's run our code. As you can see, a dark gray circle has appeared. Next, we will layer smaller circles on top of it to create a visually appealing two-tone effect. Back to the draw method. Let's create a smaller light gray circle on top of the dark gray circle to add depth to the rim. This new circle will have a radius that is 30 pixels smaller than the dark gray circle. To do this, we can simply duplicate this line of code and modify it. We just change the size and the color. So I put in -30 here for the size and light gray for the color here. Let's run our code again. Now the new circle is drawn inside the dark gray one, creating a layered two-tone effect. This way, we created an outer dark gray rim which is 30 pixels thick. It is starting to look great. Next, we will follow the same approach to add a white circle to create the main face of the clock. The white circle will be 10 pixels smaller in radius than the light gray circle, forming a clean and crisp background for the clock hands and the hour markers. Let's do it. We duplicate this line of code and we modify it. The size will be 10 pixels smaller than the previous one, so size -40 here, and the color will be white. Let's use a color built in raylib, ray white. Let's run our code one more time. Perfect. Now we can see the full clock face with a dark gray outer rim, a light gray inner rim, and a clean white circle in the center. This design forms the foundation of our analog clock, providing a simple yet elegant structure for the rest of the clock elements. Before we wrap up step number 2, let's take one more step to improve our code. Right now, the logic for drawing the clock face is directly written inside the draw method. While this works fine, it can make the draw method harder to read as we add more elements to the clock. To make our code cleaner and more organized, we will create a private method called drawFace. This new method will handle all the logic for drawing the clock face. So let's go to the header file and add a new private method. Void drawFace const. Now let's implement this method. We copy these lines of code from the draw method and we paste them inside this new method. Now we update the draw method to simply call this new method, drawFace. This refactor doesn't change how the program works, but it makes the draw method much cleaner. It also allows us to easily modify the clock face in the future without touching the draw method. Let's run the code one more time to ensure everything still works as expected. Perfect. The clock face looks just as it did before, but now our code is better organized and easier to extend. Refactoring like this is a great habit to build as a programmer, and it will help you keep your projects clean and maintainable as they grow. With that, we have officially completed step number 2. Great work! Our clock is starting to take shape. But as we dive deeper into this project, you will notice we rely heavily on classes and object-oriented programming concepts to keep our code clean and organized. If you are not entirely confident with object-oriented programming yet, or you have ever wondered not just how to use classes, but why to use them, I've got you covered. My course, Object-Oriented Programming Made Easy, is designed to make object-oriented programming crystal clear. In just 3.5 hours, you will not only learn the key concepts like classes, inheritance, and polymorphism, but also discover why object-oriented programming is a game changer for simplifying complex projects. Plus, in the course, we will build a fantastic project together, a digital life simulation. You'll see firsthand how object-oriented programming transforms a complex idea into something surprisingly manageable and fun to code. It is the course I wish I had when I was first learning object-oriented programming, and I promise it will help you understand object-oriented programming once and for all. The link is in the description. Check it out and take your coding skills to the next level. Now let's move on to step number 3, adding hour markers to the clock face. These markers are small rectangles placed around the edge of the clock to represent the 12 hours. They help structure the clock and make it easy to read. Instead of using trigonometry to position the markers, we will take a simpler approach. We will draw one rectangle starting from the center of the clock and rotate it step by step. By rotating each rectangle 30 degrees, we ensure they align perfectly with the 12-hour positions, forming a neat circle around the clock face. Once the 12 rectangles are drawn, we will add a final touch. A smaller circle will be drawn in the center of the clock to cover the inner parts of the rectangles. This leaves only the outer edges visible, creating clean, evenly spaced hour markers along the edge of the clock face. This method is simple and gives the clock a polished, professional look. Let's do it. We will create a new method to draw the hour marks, so in the header file we add a new private method. Void draw hour marks parenthesis const. Let's implement this. We will begin by defining a rectangle that starts at the center of the clock. Its width will represent the thickness of the hour marker, and its height will match the radius of the clock to ensure it extends outward. Float rect width is equal to 10 and float rect height is equal to size. Now we need to position it on the window. Typically, rectangles in raylib are drawn from their top left corner, meaning the x and y coordinates define the corner of the rectangle. However, in our case, we want the rectangle to originate from the center of the clock and extend outward. Additionally, we want the rectangle to rotate around the center of the clock, ensuring that it aligns perfectly with its hour position. To achieve this, we will use the drawRectanglePro function, which allows us to specify a custom origin point for the rectangle. This origin point acts as the reference for both positioning and rotation. We will set the origin to the bottom center of the rectangle, and placing it at the clock center, we ensure that the rectangle is properly aligned and rotates naturally around the clock's center. So let's create a rectangle struct to hold the position and the size of the rectangle. A rectangle rect is equal to curly brackets position.x, position.y, rect width, rect height. Now we need to draw this rectangle. We will use the drawRectanglePro function. drawRectanglePro parenthesis. The first argument is the rectangle to draw, rect, then the origin point. We will set it to the bottom center of the rectangle. Curly brackets rect width over 2, rect height, then the rotation, let's say 0 degrees for now, and lastly the color, dark gray. In other words, the rectangle will appear with its bottom center located at the position x and position y coordinates, the center of the clock, extending outwards based on its width and height. Before running the code, let's draw a small red circle at the center of the clock. This will help us visually confirm the exact center of the clock and ensure that the rectangle is positioned correctly. Draw circle V, parenthesis, position, 5, red. Now let's call this method in the draw method and run our code. Draw our marks. Let's run the code now. As you can see, our rectangle appears and its bottom center point is at the center of the clock. Perfect. Now let's duplicate this line and add a rotation of 30 degrees to the second rectangle. If we run the code now, we can see the rotated rectangle as well. Our rotation works. So let's now create a for loop to draw all 12 rectangles. For parenthesis, int I equals 0, I less than 12, I plus plus, curly brackets. Draw rectangle pro, parenthesis, rect, curly brackets, rect width over 2, rect height, I times 30, dark gray. Let's run the code again. Perfect. All the rectangles are drawn and rotated around the red circle exactly as expected. Now that everything looks correct, we can remove the red circle since we no longer need it for debugging. Next, let's add a white circle on top of the rectangles to mask their inner parts, leaving only the outer edges visible. Draw circle V, parenthesis, position, comma, size minus 50, comma, ray white. Running the code again, we can now see the hour marks beautifully aligned and displayed exactly as planned. And with that, we have completed step number 3 of our project. Great job so far, we are making excellent progress. And believe it or not, the most challenging part of the code is now behind us. Next, let's move on to step number 4, adding the minutes hand. To create the minute hand, we will follow a similar approach to the one used for the hour marks in the previous step. The minute hand will be represented by a thin, long rectangle. This rectangle will originate at the center of the clock and extend outward, stopping just short of the clock's edge to maintain a proportional and polished look. Additionally, we will need to rotate the minute hand to reflect the current minute. Since a full hour represents 36 degrees and there are 60 minutes in an hour, each minute corresponds to 6 degrees of rotations. By multiplying the current minute value by 6, we can calculate the exact angle needed to position the minute hand correctly on the clock face. So let's go to the header file and add a new private method that will draw the minute hand. Void draw minute hand, parenthesis, int minute, const. This method will take the minute as an argument. Let's now implement it. First, let's define the hand width and length. Float hand width is equal to 10. Float hand length is equal to size times 0.7. We make the length of the hand slightly shorter than the clock's radius. Next, let's create a rectangle struct just like we did in the previous step. Rectangle hand rect is equal to rectangle curly brackets position.x, position.y, comma hand width, comma hand length. Now let's calculate the rotation angle. As we said, the minute hand should rotate 6 degrees for every minute. Int angle is equal to minute times 6. Now we need to draw this rectangle. Again, we will use the draw rectangle pro function. Draw rectangle pro, parenthesis, hand rect, comma, curly brackets, hand width over 2, comma, hand length, comma, angle, comma, dark gray. Again, we place the bottom center of the rectangle at the center of the clock. We are ready. Let's call this method in the draw method and see if it works. Draw minute hand, parenthesis, 25. Now let's run the code. Beautiful, our minute hand works. Let's use another value for the minute to ensure that the hand aligns correctly with different positions. For example, we can test it with a value like 30 to see if the hand points to the 6 o'clock position. We change this value to 30. Let's run the code one more time. It works. With the minute hand complete, we are one step closer to a fully functional analog clock. Next, let's move on to adding the hour hand, which follows a similar logic but requires a slightly different rotation calculation. The hour hand will be represented by a rectangle that is shorter and thicker than the minute hand, making it visually distinct. This rectangle will extend from the center of the clock and point to the appropriate hour mark on the clock face. The key difference lies in how we calculate the rotation angle for the hour hand. Since the hour hand represents 12 hours on the clock, the full circle of 36 degrees is divided into 12 parts. This means that for every hour, the hour hand rotates 30 degrees. However, the hand does not jump directly from one hour to the next. It gradually moves as time progresses. To achieve this smooth transition, we also consider the fraction of the current hour based on the minutes. For example, at exactly 3 o'clock, the hour hand points to 90 degrees. 3 times 30 degrees. At 3:30, the hour hand points halfway between 90 degrees and 120 degrees. To calculate this rotation, we use the formula. Rotation angle is equal to 30 times hour plus minute over 60 times 30. With this calculation, the hour hand will always point to the correct position, smoothly transitioning between hour markers based on the current minute. If we take a closer look, we can see that most of the logic for drawing the hour hand is identical to the minute hand. The only differences are the dimensions and the angle calculations. To avoid repeating the same logic, we will create a generic method called drawHand. This method will take parameters for the hand's width, length, rotation angle, and color, allowing us to reuse it for both the hour and minute hands. Let's declare it in the header file. Void drawHand, parenthesis, float hand width, comma, float hand length, comma, int angle, comma, color, const. Now we can implement it. We cut these two lines of code from the drawMinuteHand method and we paste them into the new drawHand method. We just need to change the hard-coded dark gray color here to the color parameter. That's it. Our new method is ready. Now let's refactor the existing drawMinuteHand method to use the new generic drawHand method. We simply type drawHand, parenthesis, hand width, comma, hand length, comma, angle, comma, dark gray. Let's test our code one more time to ensure the refactored drawMinuteHand method works as before. Perfect. Everything is functioning as expected. Now let's move on to creating the drawHourHand method. First, let's declare it in the header file. Void drawHourHand, parenthesis, int hour, comma, int minute, const. In this method, we will define the width and the length of the hour hand to make it visually distinct from the other hands. Float hand width is equal to 15. We want this hand to be thicker. Float hand length is equal to size times 0.6. We want this hand to be shorter. Next, we calculate the rotation angle for the hour hand. As we discussed earlier, the hour hand moves 30 degrees for each hour and transitions smoothly based on the minutes. The formula is this. Int angle is equal to 30 times hour plus minutes over 60 times 30. Now we use the generic drawHand method to draw the hour hand. drawHand, parenthesis, hand width, comma, hand length, comma, angle, comma, dark gray. Let's update the draw method to test the hour hand along with the minute hand. Draw hour hand, parenthesis, 3,30. Now let's run the code one more time. Great. As you can see, we now have both hands appearing on the screen. Another step is now complete. We have just 2 steps to complete our project. We are making great progress. The next step is to draw the second hand. Once again, we will use a similar approach. We will draw a rectangle and we will rotate this rectangle each second to accurately reflect the passage of time. Let's get started. We will start by declaring a new method in the header file. Void draw second hand, parenthesis, int second, const. Now let's implement it. We will set the width and the length of the hand. Float hand width is equal to 5. I will make the length of the hand slightly larger than the clock radius. You will see why I do that in a minute. Float hand length is equal to size times 1.05. Next, we need to calculate the angle for the second hand. Since the clock phase is divided into 60 seconds, each second corresponds to a 6-degree rotation. The formula is straightforward. Int angle is equal to second times 6. Now we use the drawHand method to draw the second hand with a red color. drawHand, parenthesis, hand width, comma, hand length, comma, angle, comma, red. Let's test our new method. In the draw method of our class, let's call the new method to draw the second hand. Draw second hand, parenthesis, 0. Now let's run our code again. Perfect. The second hand appears. However, if we take a closer look at how the second hand is designed in our original concept, we can see that it is slightly off. The second hand currently rotates from its left edge, which isn't correct. It should rotate from a point slightly offset between the left edge and its center. To address this, we will introduce a small offset to the y-axis when setting the rectangle's origin. This adjustment will ensure that the second hand rotates around the correct pivot point. To implement this fix, we will modify the drawHand method to include an offset parameter. This parameter will allow us to adjust the y-coordinate of the rectangle's origin. In the header file, we update the drawHand method declaration to include the offset parameter, int offset here. In the implementation file, we also update the method to apply the offset, int offset here. The offset parameter will adjust the y-coordinate of the origin of the rectangle. For the second hand, instead of being at the bottom center, it will be slightly higher. So here, where we set the origin, we apply the offset, -offset. Our method is ready. With the updated drawHand method, we need to modify all the calls to include the offset parameter. For the drawMinuteHand and drawHourHand methods, we set the offset to 0, since they rotate from the bottom center. For the drawSecondHand method, we will apply an offset of 55 pixels to achieve the desired rotation pivot. Let's run our code one more time. Perfect. The hour and minute hands are unaffected and the second hand is slightly offset. All our hands are now ready. To further enhance the appearance of our clock, let's add a small dark gray circle at the center. This circle will cover the base of the hand rectangles, giving the clock a clean and polished look. Let's go back to the draw method and add this circle after we have drawn all the hand elements. Draw circle V, parenthesis, position, 15, dark gray. This creates a circle with a radius of 15 pixels, centered at the clock's middle using the dark gray color. Now let's run the code one more time. Perfect. The new circle hides the base of the hands, and our clock now looks neat and polished. Congratulations on making it this far in the tutorial. We have successfully completed step number 6. Now there's just one final step to finish our clock, and it is the easiest one yet. All that is left is to fetch the current time and set the hands to their correct positions. Let's bring our clock to life. To fetch the current time in C++, we will use the ctime library. This library provides functions to get the current hour, minute, and second. Let's modify the analog clock class to handle this. Let's go to the header file. First, we include the ctime library at the top of our file. Include ctime. Next, we will add 3 attributes to the analog clock class to store the current hour, minute, and second. Int hour, int minute, int second. In the constructor of the analog clock class, we initialize these attributes to default values, hour, parenthesis 0, minute, parenthesis 0, second, parenthesis 0 here. Now let's create a public update method that will be responsible to fetch the current time at every frame. Void update. Let's implement it. First, let's get the current time. std::time t is equal to std::time parenthesis 0. Now let's convert this time to local time. std::tm asterisk now is equal to std::local time parenthesis ampersand t. The variable now is a pointer to a tm structure that holds the current local time, including fields like the current year, month, day, hour, minute, second, and more, all adjusted to the local time zone. So all we have to do now is to get the value we need and assign it to our attributes. Now let's get the hour. Hour is equal to now, arrow, tm arrow, %12. This line extracts the current hour from the tm hour field of the now structure, which represents the hour in 24-hour format. The modulo operator, %12, converts it to a 12-hour format, ensuring that the hour ranges from 0 to 12, like a traditional analog clock. Now let's get the current minute and second. Minute is equal to now arrow tm min, second is equal to now arrow tm sec. To make the clock hands reflect the current time, we need to modify the draw method. Instead of using static values for the hour, minute, and second, we will use the time attributes we just created. So I modify the draw method like this: minute here, hour, minute here, and second here. Our code is almost ready. All we have to do now is to go back to the main file and call the update method of the clock object inside the game loop. Clock.update. Let's test it out. Perfect. As you can see, the clock now updates dynamically to reflect the current time. All the hands move smoothly and correctly, and the clock looks polished and functional. Congratulations, you have completed the project. Fantastic work! You have just built a fully functional analog clock with C++ and raylib. It is not only a great project to showcase your programming skills, but it is also a solid introduction to concepts like drawing, rotation, and working with time in C++ and raylib. If you enjoyed this tutorial and found it helpful, don't forget to like this video and subscribe to my channel for more fun and educational programming projects. Your support helps me create more tutorials like this one. If you want something more challenging, check out my tutorials on building Tetris or Space Invaders. These projects dive deeper into game mechanics, logic, and even some advanced graphics techniques. They are perfect for leveling up your skills while having fun building classic games. Thank you for watching, and I'll see you in the next tutorial. Happy coding!